All right, so I'm going to go ahead and get started. We're about a minute after the hour. People are still kind of coming in and getting settled, but wanted to kick this off. So thanks everyone for attending. My name is Justin Young. I'm going to be doing this presentation on migrating a mature application and plugin infrastructure to a PPL-based architecture. And I'm going to be digging into those terms a little bit. So if you aren't I would wager that everyone here is at least somewhat familiar with what I just said, but I'll be defining some of those things and walking you through it a little bit as well. Let me see. So how do I move forward here? Okay. So a little bit about me. My name is Justin Young. My background is actually in experimental physics. I got a PhD from Ohio State University. Since then, I've been working with Viviota, which is a startup based in Austin, Texas, since 2016, where I've been working as the chief architect here. I've been working with LabVIEW for about 10 years now. Started it in grad school, which is a pretty common thing to happen. Also joining me as the moderator here is Darren Schmidt, Viviota's CTO and one of the co-founders, who worked at NI for many years before transitioning to Viviota. Darren, do you want to say hi?
Hey, everybody. I was part of the LabVIEW team for 10 years, and before that worked on other projects and so forth. So I was 20 plus years at NI before starting Viviota. That's enough of me.
Yeah. So he's going to be managing the session for the most part. If you have, feel free to add questions, ask questions as we're moving along. I'm not going to be monitoring the chat super hard, but that's what Darren's there for. So he'll pull out questions as they're relevant and things like that. Or I might see them as they pop up as well. Just depends. Before I move on to the project as a whole, I wanted to give you a little bit of an idea about, do a little bit of a plug for our company, what we do. So we do a lot of work with, Viviota does a lot of work with engineering teams, targeted at working with them on next generation advanced vehicles and devices, specifically from the data management and analytics perspective. We were founded in 2016. Both of our co-founders came directly from NI. They split off with a project and some additional things and decided to form their own company. Our software platform that we sell is called Time to Insight. And that was created around 2017 was when we first started deploying it to companies. And like I said, for the most part, it's targeted at data management and analytics. So we are dealing with data after we don't do much data acquisition. We are working with data once it hits a hard drive and is in a file system, or once it hits a database. We have customers all across the world in automotive, aerospace, medical devices, semiconductor, very similar customers to NI and other partners. We're a startup, we're venture capital funded, based in Austin, Texas. We do a lot of work with NI products, LabVIEW, SystemLink, Diadem, LabVIEW NXG, and a little bit of Python work here and there. Like I said, we do very little hardware DAC work, primarily solving data-oriented problems. So either data at rest or data as it comes, shows up on a network someplace. Occasionally, we dig into some interesting real-time or near real-time challenges, but those are kind of in the minority. Just depends on the customer that we're interacting with. We're a small team of developers. There's three of us, three full-time developers. We have multiple contractors, people that we work with regularly, as well as working with several different NI partners out in the ecosystem, depending on what we need. And we're actually hiring right now. So if you're interested in either coming on full-time or potentially contractor, if what we're doing sounds interesting, feel free to reach out and we can have a chat. I have this little icon up in the upper right here. This is what we do with a lot of our customers. It fits into this framework nicely. So we're taking data from disk. We need to clean it, cleanse it. After that, it goes into a search engine. Some of you might be familiar with Data Finder. an NI product that's part of the System Link family. And so we provide search engine interfaces and then provide analytic services on top of that data once it's in there. So that's kind of enough about the company. I want to talk a little bit about this talk and what I'm going to be doing with this talk. So packed project libraries have kind of been a semi-popular topic over the past few years. I've seen sessions at NI Week, CLA summits, CLD summits. There's been a couple of them at the some of the other user group meetings and GDevCon as well. Mostly what I see them focusing on is what are PPLs, why you might want to use them, and how you can create a PPL-based plugin architecture for your application. The thing that I found that was kind of missing is a lot of these talks were very much introductory. They were very greenfield. So starting from scratch, I'm building a brand new application. How do I work with PPLs and create a successful application and interface layer there? What I haven't seen is how, if you want to apply PPLs or start working with PPLs in a mature application or an older application or legacy code, what are some best practices and how does that work? How to deal with common code migration in PPL. So one of the things that we have, at least in our project, is we have a lot of reuse libraries and a lot of common code. So how do those fit into the PPL structure, and how do you build things with them? And what do you do if it's a large application? And I'll talk a little bit about what large is for us, at least later on. What this really is a case study. So over the past couple of months, we took our primary application, Time to Insight, and we basically turned it into a PPL-based architecture with a plugin layer as well, all using PPLs. And like I said, it's a large project, thousands of VIs, many hundreds of libraries and classes. And there are reasons why we decided to go down this route that I'll talk a little bit about what the motivation is, why we did it, and we'll talk about the good, the bad, and the ugly is what I put in there. Like I said, feel free to ask questions through Darren or through the chat. And hopefully, if I've timed this right, we'll have 5 or 10 minutes at the end of this presentation to chat, ask questions, and then there's a breakout session directly after this as well. That's in the there's a separate session room for breakouts directly following talks. This is not designed to be a comprehensive guide to using PPLs. There are other presentations that are better suited to that, and people that have spent a lot of time in creating guides and things like that. And I'll reference a little bit of that inside of here. A couple other caveats. This is a very active application. We started developing it in 2016. It's been modified constantly since then. It's been re-architected a couple of times, refactored a couple of times. It's very much a live application. And a lot of it has been developed with, real-time customer constraints. So there were times where we had to choose between what is good long-term and what gets us the customer project solved and out the door tomorrow. That happens in the real world. And so you'll see a little bit of how that played out in this presentation. Everything that I'm going to talk about here is in LabVIEW 2018. I know that there have been a lot of improvements that NI has made with PPLs, VIMS, other features in 2019 and 2020, but we were not able to upgrade our code base before we kind of went through this process for a couple of reasons that I'll get into later. Now that we've kind of gone through this process, upgrading and migrating to 2020 is actually pretty high on our list things that we want to do. But again, this is a real life concern. You know, older applications or long-lived applications often are not in the latest version of LabVIEW. We have, you know, like I said, we aren't working with data acquisition, and so we don't have to worry about drivers a lot of times. So we have a little bit more flexibility in upgrading LabVIEW versions than I have in some other projects that I've worked in, where you're severely limited by what drivers are available for what versions of LabVIEW or things like that. Final caveat is we don't claim to be the experts on this process. So we did things that we found worked for us. We found, you know, some things came from the forums, some things were never discussed on the forums. You know, I had conversations with the people on the topics. At the end, it's what worked for us, and I'm trying to pass on some of that knowledge. So I've already done a little bit of an introduction. The next thing I'm going to do is I'm going to do a bit of a packed library primer. So this is not going to be long. Like I said, there are a lot of other presentations that dive into this in a lot of depth. I'm going to talk a little bit about our software platform, why we did some of the design decisions between what we did, when we did it, and how we did it. When we actually went to make the migration to a PPL-based application, what challenges did we encounter? And how did we solve those challenges? And then some results and conclusions. So packed project libraries, very briefly, we're going to talk about what are packed project libraries and why do people use them. Like I said, this is not all-inclusive. There are some very good talks out there. Specifically, there was a talk in GDevCon by the StudioBots guys on building PPL-based applications. Very, very good talk, and it's available online that you can go and download it, look at the slides, watch the presentation. Then there was another one the last NI week that we actually had by Zebra Technologies, where they also talked about packed project libraries, and they dug into some interesting aspects as well, specifically related to how you deal with paths inside of packed project libraries. That was very helpful. And then there's a standard kind of set of resources online, you know, LabVIEW manuals, some white papers by NI, and some kind of, I'll say, classic posts on the NI forums about how these things work. I've given the tiny URLs here to make them easy to take a screenshot and type in if you want to. There's a secondary slide here that has the full address as well, that when this gets posted online, it'll have it. So before we talk about packed project libraries, I want to talk about libraries in general. I think that a lot of people use libraries now. I think it's generally considered best practices in LabVIEW to use libraries. You know, I have this kind of screenshot here about what really is going on, why you might want to use libraries. On the left is kind of an old, what you might see in legacy code or old code, where you load it, and there's, you know, auto-populating folders. Each device has its own folder. And on the right, I have a contrasting view with packed libraries, where now everything is kind of virtualized, and we have these libraries that contain the VIs targeted at different functions. A lot of times you'll have libraries with classes in it as well. While our code is very heavily class-based and object-oriented, it's not required for certain aspects of this, but it's still useful to have libraries whether you're using classes or not. Libraries help organize code. They also provide namespacing. So whenever you're using a library, the library's name is now part of the VI name. And I have an example of that a little bit later on, but it's basically library name : VI name. And so that allows you to have VIs with the same name in different libraries. So one of the things that you'll see here is on the left, there's this conflict between there being two creates for the different loggers. And on the right, the creates aren't conflicting anymore because they have additional library namespacing. With libraries, you get a common VI template, which is nice. Generally, they're just easier to work with in LabVIEW. You can kind of treat the library as one large object and move it around and work with it that way. And then you also get scoping, which it can be really handy as well. So you can create things that are public, so they're available for everyone to use. This is really useful for APIs. You have private things so that only members of that library can access that VI or control, and then you have community. So other VIs that are in the community can work with it. And I think I've left one out there as well, but I don't. I mainly use public and private a lot in my own coding. I don't use the other two very often. Difference between packed project libraries and a regular library. In this case, first and foremost, there's that little P on the end of the extension. Packed project libraries are compiled. So in a LabVIEW library, you have many VIs that are on disk in some sort of folder structure. In a packed project library, everything is compiled and placed into a container. Conceptually, this is very similar to the old LLVs that used to be used, where you would put a lot of VIs into a single container that was essentially kind of a zip file that you could pass around. But in reality, this is closer to a LabVIEW specific DLL, where you're packaging all of these library functions into a single file and it can then reference it from LabVIEW. So it is compiled, so that means it's read-only. And the other aspect of this is that it's actually OS and bitness specific. So if you compile a PPL, it's only usable on for the LabVIEW bitness that you compiled it for and the LabVIEW OS you compiled it for. So you might have to have multiple versions of the same PPL compiled for different OSs and bitnesses. The other thing that's kind of important about packed project libraries is how it deals with dependencies. So in regular libraries, it's just a reference to the dependency. So if you have something in VI-lib that you're calling, it'll reference that by the way that LabVIEW tends to reference things. Once you build a packed project library, all of those dependencies are included inside of the packed project library, except for two cases, one of which is if it's referencing another packed project library, it'll be, that reference is now external. If you're referencing DLLs, that reference will be now external. All of those dependencies are included in inside of, hidden inside of the packed project library, inside of the path structure in there. So you can't see them. So the interface that you get with the packed project library, you won't see those kind of hidden dependencies. I see, so Paul asked, what about LabVIEW versions? That's a good question. So prior to, I think, LabVIEW 2018, you had to compile it for each LabVIEW version. From 2018 on, it might have been 2017, there's now the option to make packed project libraries forward compatible. So if you compile something for 2018, it will still work when called from LabVIEW 2018 and 2019 and 2020. In my own limited experience, I find that this works most of the time. Occasionally something changes and you will have issues and you'll have to recompile it for the new version of LabVIEW, but most of the time I found that it works well. It is 2017. So why do we want to use packed project libraries? So that's the difference is why do we even care about this? So if we look at an application, and this is a kind of simplified diagram of some of the components of what exists in our main TTI application, we have lots and lots of libraries. As the application matures, you end up including more and more code in this executable as you add new features, as it grows. And most recently, we ended up with an executable that was about 65 megabytes. It would take quite a while to compile, and it took a long time to load into memory. By long time to load into memory, it would take between, it would take 30 seconds before you even see the splash screen show up, and by the time everything was kind of loaded and working, we would be about 3 minutes in. Compile times for us were on the order of 15 to 20 minutes, which I know I have heard horror stories of people taking hours to compile. but that is not necessarily the case for us. When you move to a PPL, when you PPLize an application, though, what you end up getting is all of these libraries now become external dependencies and are loaded as such. So the only thing that is in the executable is kind of the core code that you're running, and everything else is, like I said, it's like you using DLLs. All those functions exist elsewhere on disk. And so you may load the main VI, and then it calls dynamically all these other things that live externally on disk. This becomes very handy because now our exe executable is much smaller, it loads much faster, and it compiles much faster. Our compile time is it's only a couple of minutes now. And it's much faster to compile, much easier to work with. Some of the other advantages that you get out of this is all of the components are individually versioned. So back here you can see that, in the first case, you get one version for the exe. In the new picture, you have a version that's included for the exe, and then all of your libraries are versioned as well. And that's something that the OS even recognizes. So you can see explicitly what version of the PPL that you're working with, and that makes upgrading and updating very nice. You only recompile libraries that change. So, like I said, when you're doing when you're compiling the exe, you compile the exe. You don't need to go back through and recompile all the libraries unless something explicitly changed. And if you change one library, you don't have to go back and recompile the exe. So you can update, if I'm down here working in one, like my common code over here, and I upgrade a function so that it's more efficient. Maybe it's parsing a string better or something like that. I don't need to recompile the main executable. I just need to update the common packed project library and distribute it to my application or my customers, and it'll work. Like I said, you get faster build times, compile times, and load times. And this is very nice. And you get faster. So this can also help if you have very large projects that are calling lots of libraries, lots of classes. When you load LabVIEW, you always, and LabVIEW has gotten better about this in more recent versions, but it used to be, you load a large project and then go get a cup of coffee and come back and it's done. These times are greatly reduced when you're working with project libraries. Faster build times I already talked about. It also is a really good way to deal with dynamically loaded plugins, which ends up being a huge deal for our particular use case. And I'll talk about that here in a few seconds. I've been seeing a lot of stuff happening on the chat. Are there any questions that weren't kind of answered, Darren, that I should talk to before I move on?
There was a question that I think was kind of danced around related to Git, which was about versioning, and so if you think of it as standard library stuff, the versioning matches to that. So there's nothing for PPLs that are unique from a Git perspective other than you're getting a compiled piece of code that needs to be managed more like a binary than from potentially an SCC piece of LabVIEW. Is that correct?
Yeah, so PPLs are treated as binary objects. I keep those objects outside of, so I keep the projects in source code control, but the actual builds I leave outside of source code control. And in fact, I'll talk about that a little bit, specifically when I get to the how we deal with this huge chunk of common code that we have in our projects, and how I deal with versioning and controlling what version of PPLs we're using. This is still a little bit new for us, so we're still exploring what the right way to deal with some of these things are. But like I said, I'll talk about that here in a few minutes.
And then the other piece was much more tied to the fact that they're dynamically loaded. The question was around the idea that PPLs get essentially unloaded from memory when they're not used. So this is some linkage stuff that I think gets pretty unique.
Yes and no. So you can create an architecture that loads PPLs and unloads them when they're done. There are some intricacies to that. Typically, when you bring a library and a class into memory, LabVIEW leaves it in memory until the application is done, or until the caller no longer, the caller is out of memory. And so there are some very clever things that people have done to make this work. We have not integrated that into our own project yet because it didn't work well with a mature project, because we couldn't abstract out our APIs to that level, because you essentially need to call, not only is the API abstracted, but even calling the API ends up being abstracted, and it becomes a little bit tough. I'll flash up the references here in a little bit again, but the very first presentation on that list talks about that actually. The other thing that I also want to make a distinction here between libraries and plugins. When I'm talking about libraries, I'm usually talking about something that's essentially reuse code. So these are dependencies, whereas plugins are dynamically loaded instances of like an interface. So in this diagram here, kind of the interface class is an instrument. There are several concrete classes of this, power supply, multimeter, switch, and temperature sensor. All of these are types of instruments. They can be loaded as plugins for the system. So if we're running one configuration, you use one set. If you're running another configuration, you run another set. Then there are a set of generic dependencies that kind of anything can call or anything can access. These might be like error handlers, JSON parsing, loggers, lookup tables, REST web clients, any number of things like that. I make this distinction because it ends up becoming important from a developer perspective, how you kind of separate out these things and what you turn into packed project libraries and what you don't. When you look at these different organizations, the way that this ends up kind of falling out is if you were just using libraries and not packed project libraries, at least for us, we ended up kind of having a primary project that had the main executable and the interface classes, and then we had secondary projects that dealt with the plugins. All of the common code was inside of VI lib, managed by VI package manager. And when we deployed, we ended up with an executable, and initially we were using, when we first implemented our plugin layer, we were actually using source distributions. Ignore the custom extension here. It was just to obfuscate it a little bit for customers, but they're essentially zip files with source distributions. And yes, so I saw the mention of VIPM for PPLs. I will talk about that in depth because this ended up becoming a big thing for us. When you switch to PPLs, you end up having a slightly more, it's both more complex and simpler actually. You end up having a separate project for the different interfaces that you have, where you're dealing with a source code. So you have a project that has an instrument.lvlib. You turn that into a PPL, and then that PPL is then used in both the primary project and the plugin projects. Again, I'm not going to go into the details of how this build process works because I could spend a whole hour just on that, and I don't, and it's covered other places. And so that's how you deal with the plugins, and when you show that on disk, you end up with something that now looks like your executable. You might have a plugin folder that lists all your plugin interfaces and all the individual plugins inside of it. The question then becomes, how do you deal with this common code? Like I said, this ended up becoming a bit of a sticking point for us when we first started going down this path because we have a lot of common code. We have a lot of reuse libraries. The stuff in VI lib, you could copy it into each PPL. So everything that calls these libraries in VI lib could essentially include it inside of itself, and it'll be fine. It will make these PPLs bigger, but it namespaces them separately, so it would be okay. The problem you get into there is that you get a lot of bloat. The PPLs become large in size. There's also a little bit of a challenge because the namespacing changes. So if we have a common logger class, this now goes from logger.lvlib : logger.lvclass. you end up getting that packed project library namespacing at the very beginning of this. That's okay for the most part, unless you're dealing with classes that you share between libraries. Now, if you include this in the back end, you end up getting that separate namespacing. So if you include a logger class and different things work with that logger object and it gets passed around, now you have essentially separate namespaced instances of it. The digital multimeter has its own instance of it, and the instrument has its own instance of it. And they're no longer compatible. LabVIEW treats them as completely separate objects. And so you can't just pass it from one library into another library. Again, this can be okay if it's all just internal to the library or things like that. But for instance, our application is actor-based. So if you have messages that are going between different libraries, if those messages are not included in the library, if those messages are included as dependencies in each one of the libraries, they're no longer compatible, and your actors can't talk to each other. And this becomes a lot of problems, causes a lot of problems. So the alternative is to essentially turn all of your common VIs into, all your common libraries into PPLs as well. And this is the route that we took. There's, again, some challenges here that I'll talk about in just a few seconds, but this can solve the problem, and it solves it pretty successfully. So now I end up with a slightly more complex folder hierarchy when I'm deploying. I have the executable, I have the folder with all the plugins, and then I usually have another folder that's dedicated to kind of all the common core stuff. And this works. You end up with another problem though, particularly with fairly mature reuse libraries deployed through VIPM. If all of your palettes were built inside of VIPM, what happens? How do you continue to develop these applications or plugins when suddenly all of your linkages are no longer correct? If your palettes are referencing the libraries, the raw libraries on disk, and your project has the packed project libraries on disk, they're not compatible. And this causes a lot of problems from a development perspective. And so this was one of the problems that we had to solve. And I'll talk about how we solved it in some of the coming slides. Before I dive into actually how we solved these problems and some of the other problems that came up, I want to give you a little bit of background on the actual application that we were working with. Like I said, it's a very mature application. It's been around since 2016, started out as a proof of concept and evolved from there. We deployed it to our first customer in 2017. And from different people have different definitions of what a large LabVIEW application looks like. And it ends up becoming contests about who has the most VIs or libraries or things like that. I don't really care. From my perspective, it was a large application for us to work with. I know that people have larger applications and things like that. It's, like I said, it's not really a contest for me. But in this case, the main application had about 3,000 VIs, 200 classes, and 85 libraries. Like I said, we're actor-based, so we do have a lot of classes that are like for messages, which is why there are so many classes compared to libraries. But even more than this, though, the main application has that. Our reuse libraries are actually almost double the size. So our reuse libraries have almost 6,000 VIs spread out across 300 classes and 125 libraries. And so this is why the reuse stuff and the dependencies ended up playing such a big part in solving this for us. It's also a requirement that we support a plugin infrastructure. So every customer that we deploy to has the same executable, same built executable, otherwise it becomes unmaintainable. This is one of the re-architectures that we did kind of early on. And each customer has their own subset of off-the-shelf and customized plugins. And so what the strategy that we went with is we have one plugin interface that can be one very generic plugin interface that tells us how to load things and display things and close it out. And then we use this kind of all over the place as an interface. our plugins all fall out of that interface. I'm not going to go into the depths of our plugin infrastructure because I don't think it's important to how we move forward, but that's what we're doing. A little bit more of the project history. Like I said, we started off in LabVIEW 2016 as a proof of concept, and it originally started off with a Q-driven state machine. It was designed as a fast proof of concept, just to show that we could do what we wanted to, and that it had value to customers and things like that. Around 2017, we refactored it, turned it from a queue-based state machine to actor-based. We aren't using the NI actor framework for reasons that could be a whole different talk. But it is an actor-based framework, so it's very similar. It has message classes, it has actor classes, things like that. We deployed to about 2 to 3 different customers, single main code base for all the customers. That was helpful, but we were still having multiple executables depending on the plugins that they needed. It wasn't plugins at the time. It was plugins from a development perspective, not from a deployment perspective. In 2018, we transitioned to add true plugin support. We were deployed to, we had about doubled our customers at that point again, still actor-based. Now we added in a plugin layer. We went with a source distribution plugin layer, and I'll talk about what that means here in a few seconds. So now we were deploying single executables for all customers, and it was definitely an improved quality of life for our multiple developers. Now in 2020, towards the end of 2020, we've migrated to PPL-based architecture for everything. So our actors are all PPL actors. Our plugin layers are all PPLs, and we've again about doubled our customer deployment since then. And I'm going to go into the reasons for the redesign here shortly, because I saw one of the earlier questions was why is it even worth converting a mature application? And it's a custom actor framework from us. I saw that question in there. So why did we make these? So in 2018, we moved to a plugin architecture. We found that a growing number of executables, it was just becoming unmanageable. Wanted all customers to be off of a single EXE and have different projects per customer. We toyed with the idea of going to packed project libraries at the time, but after poking around a little bit, it basically seemed to us that this was going to be a lot of trouble, and we weren't sure that it was going to be worth it. We had talked to people, found that, especially with the dependencies and the actor basis, it seemed like it just wasn't going to work very well. So we opted for kind of the older method of plugins, which are source code distributions. So the idea is that you create a distribution of source code, you include the plugin, you include the specific plugin that you're working with, you exclude the interface classes. There's a couple good blog posts on this and a couple good white papers on it on how to make this work. You end up deploying, on disk. This looks like a folder with VIs in it, and you create a zip file. In theory, it's very easy, very straightforward, and for us, it worked for about 10 to 12 months. And then what ended up happening is we started hitting major issues. As we were evolving both the main EXE and the plugins, the line between what needed to be included in the plugins, what needed to be included in the EXE, and what needed to be excluded from these different places became really fuzzy. Vim usage these were really exciting from a development perspective. From a distribution perspective, it became a nightmare. All of the rules transitioned to more guidelines. Just lots of problems. You can see over on the right, we actually have one of the build specs for one of the plugins that we managed to create. You can see the collection of stuff that's almost randomly selected and exclude down here. The options for the additional exclusions became very confusing. and didn't really work that well. So we were having a lot of problems, and a lot of times these things would build correctly, but as soon as you would call them from the executable, it wouldn't work anymore. And we would have no idea why. It would just tell us that the library was broken, and we didn't have really any good tools to get in there and figure out why the library was broken. So this came to a head. We tried upgrading to 2019, had additional problems. Really, what the straw that broke the camel's back is we had a major update that went out to our executable and some new plugins, and it took us a full 8 days to get everything working again, just from a compilation perspective. And even smaller plugins were taking 1 to 2 days to compile and run correctly, and it was just no longer sustainable. So we were literally in this type of environment, and we decided we're done with this. I had in parallel, because I kind of saw this coming, had started playing around with PPLs in a secondary project, I had become convinced that this was the right way for us to go. So when we went to convert it to PPLs, when we made that decision, we had some goals. The biggest goal was we needed to reduce the compile time. We wanted to reduce the time to load the executable, reduce the size of the executable, support current workflow as much as possible, simplify project folder structure if we could, and some of our long-term goals where we really want to have better support for proper DevOps and CI/CD, provide SDKs for customers to develop their own plugins, and transition to LabVIEW 2020. At this point, what I'm going to go into is some of the issues that we encountered while going through this process and how we ended up solving them. The first big issue that I alluded to earlier is what do we do with our reuse libraries? This was because we have so many and because they're kind of used by everyone and were distributed by VIPM, this became kind of a critical issue for us. We had to support the palettes because that's how we do a lot of our coding, either from quick drop or from the palettes as we need it. We wanted to not break existing code as little as we could, or as much as we could. Wanted to still maintain compatibility with VIPM. Had to support VIMS, which were becoming more common. Had to support multiple bitnesses. Sometimes we're compiling for 32 and sometimes for 64-bit LabVIEW. This is something that we could not find good documentation on anywhere. There are a couple strategies that we found online, which the two main ones we found were embedding palettes into libraries, and they would be then recompiled and re-referenced in PPLs. I'm not convinced that that works, first of all, because I saw conflicting reports about it not working. And second of all of our palettes were created using VI Package Manager, and that doesn't really work unless we want to recreate all of our palettes in LabVIEW itself, LabVIEW natively. The other thing that we found that we could do is just abandon the palettes and work with things directly inside of the project. So load a PPL and then work with it. Neither of these really were ideal for us. So we took a slightly different approach. We made the decision to split our libraries, our common reuse libraries, into two pieces. So now we have kind of a core code library and APIs. We had already started going down this route because of issues that we had encountered with VIMS and interfaces. So we kind of pushed forward and finally separated this. This was primarily for stuff with classes. If you aren't dealing with classes, this is less of a concern. The core libraries are built into 32 and 64-bit PPLs. We zip them up into zip files that include the bitness, and we put them in a PPL builds folder. All of that goes into a VIPM package, which we created a rather simple post-install, post-uninstall VI that looks at the bitness of LabVIEW and installs it to VI-lib, a common location in VI-lib. So it unzips the correct bitness into that library. And then is, on the post-uninstall, we remove those PPLs. This got the PPLs into the right place, of the right bitness, into a place that everyone could then reference without having to worry about creating additional folders on the computer and things like that. We then actually created a secondary VIPM package that is just the APIs but with the core libraries replaced with the PPL references. So it's one of those things. We loaded the library, the API library, did a right click and replace, and it swaps all of it replaced all of those references with PPL references. Build this into a library, and it does an overwrite when it's installed, and now you have palettes that reference PPLs. And this worked really well, actually. It also gives us the ability to turn on and turn off the PPL usages. All you have to do is someone muted me, and I'm not sure why. That was kind of weird.
I tried to unmute you.
So. Okay. So I only have a few minutes left. I'm going to go through the rest of this. Actually kind of speeds up a little bit. And like I said, I'll make these slides available so that you can look at them. Because at this point, it becomes very much kind of a reference material, which can be very helpful, I think, for people, for our experience. The second issue that we ran into was circular dependencies. So you can't build PPLs if you have a circular dependency. The biggest cause of this for us was type defs. So having type defs that were created in one library or one class and are then referenced back and forth. This has lots of effects and lots of problems with LabVIEW, but the problem is that they're hard to pick out. They're hard to find, and you don't really notice them until you go to build like PPLs, and then it crashes LabVIEW. The way we ended up solving this, the best way that we found to solve this is start with a blank project, load in the library of question, and see what loads in the dependencies. So you can see on the right, this is what happened when we loaded one of our interface classes into memory, kind of when we first started down this track. And it essentially loaded the entire project into memory. On the left, you can see what happened after we were done. Nothing in the dependencies, essentially. And that's what it should look like. It would be very helpful to have a tool to find this, and apparently something like that is coming for NXG, but it doesn't exist in current gen. We found lots of LabVIEW crashes. One of them happened on, we would right-click on LabVIEW, right-click and do the replace with PPL operation, and LabVIEW would just crash. Hard crash, no message, no nothing, just was a problem. Sometimes this was because of circular dependencies. Sometimes it was because the PPL was broken, which could be solved with, can be validated through unit testing and or just loading it into a blank project and see what happens. And sometimes it just happened. And so I think this is what happens with the anti-actor framework in 2018 as well. And in that case, we just had to do a manual replace. One of the other major issues we ran into is classes that were called by other classes. When you do the replace in PPL, LabVIEW in the class data replaces it with a generic control name. This is completely unhelpful and can break a lot of code. It results in broken accessors because LabVIEW can't figure out what class it's supposed to refer to. What we ended up doing for this is we wrote a small utility that goes through, and before you do the replace, it goes and pulls all the names of all the objects inside of the classes and writes them to file. And then after we do the replace, it compares that to what the result is and fixes any names. Sometimes we still had to go back and manually fix accessors, but that was a lot, helped a lot. Something else that we ran into is compile errors. Occasionally, after we did a replace, LabVIEW would just suddenly stop compiling VIs with completely unhelpful messages, other than telling it that it just didn't work. It turned out that there was a surprisingly simple solution to this, which is, again, it's if classes are referenced by property nodes, that was the problem. So just changing it to a different item and then changing it back solved the problem. Again, stuff that's relatively simple, but the error messages are just completely unhelpful. We found a weird one with if you had something as a friend of a library and then compiled it, the replace doesn't affect that. And this gave us, it wasn't anything that was breaking, but it gave us some weird messages that it took us a while to solve. Finally, there were a handful of smaller issues. The first is that sometimes if the PPL contains type defs that are referenced, when you do the replace, it will reset the type defs to default values. This was very inconsistent for us. Sometimes it happened, sometimes it didn't. It can be especially frustrating for LabVIEW, like block diagram constants that are enums. And so you think you have one enum on the block diagram and it ends up being a different value. Some other problems, sometimes the replace classes just go missing, and in this case it's going to be a search through the errors and fixing the ones that manually need to be fixed. Sometimes classes compile badly. Again, there was no real rhyme or reason to why this seemed to happen, and it was solved by just building the PPL again. VIMS are a problem. I love VIMS, but we had a lot of problems with them. They can't be public in PPLs because VIMS compile at edit time, and you can't compile a PPL. PPLs can call VIMS from disk. Sorry, that's a typo. That's completely fine. However, occasionally there are problems when you go to compile. The things that we found that helped are include polymorphic instances in the build options, explicitly include the Vim itself, and avoid nested VIMs. That was one we couldn't get around. Nested VIMs just ended up in crashes. A note on testing, like any refactoring effort or LabVIEW upgrade, test frequently, test before, have unit tests as much as you can. A lot of times when you're building PPLs, it's very handy just to open up a new project and throw the PPL in there and see what happens. If it loads correctly, chances are you're good with the build itself. If it loads incorrectly, you'll know pretty fast. Real fast, you know, I'm already a little bit over, and I'm pretty much done. From our side, what type of effort did this involve? I took this on as kind of a side project, so I was working on it as I had time. It took me about 5 to 6 calendar weeks, about 60 hours total. And to do this, I resolved the reuse code stuff with PPLs, resolved the VIPM stuff, replaced the reuse code in the primary project, broke the primary project into mini projects for the different interfaces, ended up with about 10 different smaller projects for the different interfaces and plugins, debugged issues listed in the slides, then started rebuilding and testing everything. Once the yellow items were completed, the final stuff ended up being pretty fast. Didn't have nearly the challenges of building PPLs as I did with the source distributions. Revisiting the goals, like I said, reducing the time required to complete compiled plugins. Did that. The load time to fully load the application and all plugins went from about 3.5 minutes to 2 minutes. I believe that there's further room for optimization there. Reduce the size of the executable from 65 meg to 30 meg. Again, there's additional things that we have not turned into PPLs yet that would be future things. Supported the current workflow as much as possible, simplified the folder structure quite a bit. The splitting up into different PPLs is really helpful for DevOps. I'm looking forward to getting that better integrated into our system. And the last couple things we're still working on. Next steps for us, you know, we still have some portions of the code that need to be PPLized. There is the ability to load and unload plugins on demand, and we're working on that. We might do that. We haven't decided yet. There's some cleanup to the build process that has to happen from our side. We want to migrate to 2020. This becomes important to us, and we need to finalize the testing and deploy to customers. I know that you guys are asking a lot of questions. I think Darren is recording those. We're going to jump into the side session here, probably like right now, because we're out of time. The final thing is it worth it? It was a lot of work, and it's still very early after we completed that work. We just got to kind of a testing build, a real testing build that we could test on everything last week. But so far, I tentatively say yes. The amount of build time that it saved from having to do these source distribution plugins was immensely helpful for us. And then I have a set of resources here. I recopied these things. So I'll post these. I'll get these up into the LabVIEW wiki once that kind of happens. I think at this point we're going to shift over into the separate sessions meeting. If you guys have questions, let's switch over there, and I can answer those questions as they come in. So take like I'll be on and I'll switch to there in like 1 to 2 minutes. So thanks very much for your time, and I'll talk to you guys in a few minutes.